syntax?
Oh, syntax means we're entering something in wrong. Can I see?
Yeah.
Let's just go to.
Oh, you know what I mean? It doesn't seem
There you go. Somewhere else. Ah, question. Great question over here. Why is there a space? There should be no space. Yes, there should not be a space. When you press zoom 9, the TI decides the window it's going to decide on. Let's go in and finagle it so there is no space. So I'm going to press the window button. It has made the X-Min 69, which I think we should make that 69 as well. Now here's the goofy part. It makes X max 73.8. The largest vote was for 73. This might not make a whole lot of sense at this moment, but make it 74 for a max. I want to come back and explain why. I think this works on the 89 as well. I think it's the same reason, Jacob, on the 89. Make the scale 1. 0.8 is weird. That's why you have your gap, because it breaks your window up in 0.8. So if you make it 1, and then press graph, you'll actually see the whole window with this gorgeous freaking bell curve. Almost perfect. I mean, it's kind of ludicrously perfect. Thank you. So there's the idea. Now here are the votes for 69 inches, 70 inches, 71 inches, 72 inches, 73 inches. Those are your votes. Now the reason you set your X max to 74 is because, technically speaking, the number 69 is right here. And that's the number 70. 71, 72, 73, 74. But the way the TI tallies stuff up, it starts with the low value and goes up to the upper value but doesn't include it. So if you press trace on this, it'll tell you that 2 of you gave me a data point between 69 and 70 but not including 70, which would be the two 69s. So it's our way of kind of cheating to get discrete-ish data into a non-discrete continuous number line. Fair enough? We'll do it constantly as we go through the rest of the course, so we'll have more practice with that. And Excel is a much better tool anyway, but as far as in class goes, you'll constantly see me putting one more in the top because of it. Because Jacob, if we put 73 as the high value, we'd lose Jacob. Watch what happens. If I make 73 be the max, his bar is now gone because it's over here. It's off the window. So you have to give it one more to kind of truly capture that. Cool! So this is almost a perfect bell curve. I mean, this is ludicrously gorgeous. So now here comes, thank you for creating bell-shaped data. What I want to talk right about now is one way to quantify outliers. Do you guys think there are any outliers on this data set? Do you think Jacob 73 was too big? It's the largest, but is it too big? What do you think? Gut feeling. I heard one yes, a couple no's. How about this says 69? Are they too low? Yeah. Prove to me they either are or aren't.
We have to measure you.
Say that again?
We have to measure you.
Well, how about 5'11 and a half? So my true height is essentially here. So, good. So what Danielle is saying is the outliers would have to be too far away from my true average. Or, better, the sample average collected. Thank you for that. Let's come back to that if it's okay. I love this point. Lauren, go.
Majority of the data is in the middle three, 71, 70, 71, 72. Like a significant more amount.
You guys, believe it or not, you're both saying the same thing. Both of you are saying the same thing. Danielle's point was, well, you have to know how tall you are first. Well, here's the problem. You're never going to know how tall, when I say how tall, you're never going to know where the center of your population is. You're going to draw a random sample from your population. And that sample is going to have a center. So the question is, are the data points too far away from that center? So define too far away. Good.
You're talking about physics here.
Good. Unfortunately, the problem with 5 standard deviations in the statistics world is the tolerances are much looser than the physics world. What we just heard was the 5 and 6 sigma idea in physics and engineering. The idea that 6 standard deviations is now acceptable for a range of values. That is not what happens in research statistics.
Okay,
because, no, but you're correct.
Within 2.
That's research statistics.
Right.
Research statistics says if you have, it is a big if you have bell-shaped data if you have bell-shaped data, and this is a big if. This only works if you have bell-shaped data because guess what statistics we're going to use? Think back to your last exam. When can you use, when you have bell-shaped data, which statistics are kind of fair? The average and its, thank you Emily, the average and its standard deviation aren't misleading when you've got bell-shaped data because they're essentially where the typical data points are. You start slapping outliers on there, two extreme outliers start getting pulled. Now that's not to say that there aren't outliers on here. I understand that 73 isn't that far to the right and 69 isn't that far to the left. But remember, since the data is so tightly clustered, the standard deviation will be pretty small. Good, there's two things to think about. There's two things to think about here. Every bell curve has tails. And the tails are relative to how dispersed the data is. Good.
We're talking about the frequency, right? Not the...
Have to. How frequently was 69 versus 72 versus 73? Good, let's come back to that.
That's pretty, 69 is pretty insignificant, and 73 is pretty insignificant compared to the...
Let's give it a measurement. Let's get, rather than, I mean, visually it looks insignificant,
yeah.
But does it hold up to analytics? So here's what we do. If you have bell-shaped data, the atypical data is outside of 2 standard deviations. That's a definition. Why? Because it's been handed down to us. I'm not saying that's a good reason, FYI. I'm not saying that's a good reason. Just like I'm saying I don't think Six Sigma is always a good reason in industry. It's just what's been handed down to us. If you guys have ever read research journals in sociology or psychology about p-values less than 5%, it's the exact same thing. Because how much data is within 2 standard deviations when you've got roughly normally bell-shaped data? 95%. By definition, outliers in this respect are called the extreme 5%, 2.5 up, 2.5 down. I saw a hand, I thought. Laura, was that you? Go ahead.
I don't think they're outliers.
Okay, let's quantify it. Again, I'm not, the thing about outliers is it's easy to call a large data point an outlier, but it's hard to quantify unless we apply a metric to it. Here's a metric. Can we calculate the average and standard deviation for this data set? Well, yes. Let's go do it. Let's go do it. Okay, so we'll leave our graph screen behind. We'll leave our graph screen behind and calculate the 1-bar stats. Remember what Danielle said? Don't forget list 1 and list 2. Got to do them both, right?
Oh.
Right, if you just do it right now, it's going to give you an answer. It's also going to be wrong. Well, that's the problem is that it only thinks that 5 people voted.
Okay.
If 5 people didn't vote, about 20 voted. So we have to make sure we go 1-bar stats, L1, comma, you can't see that, can you put it up higher? 1-bar stats, L1 is where your data is, but don't forget your frequencies. Don't forget the frequencies too. They have to be included as well. Here we go. You guys guessed I was around 71 inches. Your standard deviation was about 1 inch. And your standard deviation was about 1 inch. With me so far? You see where I'm going at?
Can you remind me which one is the standard deviation?
Yes, well these are both standard deviations, but this is what we're going to pay attention to because that's our sample. So for my height data, my height stats, according to you guys, my X bar, you pegged me at 71 inches, which makes perfect sense. Like I said, it's almost a perfectly bell-shaped curve, which is staggering. And you pegged me at plus or minus 1 inch, it looks like.
I'm sorry, just really quick. When you're looking at data like this, do you always round to the 10th?
Oh, well,
Or is it kind of just that's what you do?
this is a bit, I'm going to truncate all the decimals because I told you to mark my height to the nearest inch.
Okay.
So I can't accept any more precision. I can't claim 70.9 inches if I asked you guys to round up to the nearest whole.
Okay.
Now don't worry about that too much. I try to tell you guys round to this, round to that, round to this. A lot of times it's irrelevant because we're dealing with discrete data. So don't know. I've seen rules implemented that are kind of bogus, but don't worry about that. If you're ever concerned, I'll tell you what to round to. If not, just round to what you think is right. Honestly, I'm not going to knock out sig figs in here because I mean we're not measuring a whole lot. Cool so far? So this tells us something. Going back to our screen, it tells us where our average is, which is exactly where we thought it was. We thought it was at 71 inches, and it is. right? Good, Richie. Now if we start going around, we're going to Danielle's, how far away from my average height are we? Well, my average height, as I said, you guys missed it by a smidge, but that's okay. That's okay. You can miss it by a smidge. That's the whole point of sampling. You are going to miss what you're looking for by a smidge. The idea is, can you smudge the range far enough to catch the smidge? Yeah, 95% of the time you can. That's the point. But we're trying to see if there are any extreme values. And Laura, you're saying no because there aren't any, are there? If you go out to 1 inch, 2 inches, you've gone out to 73 inches here. That's out x bar plus 2 s's, yes? And if you go down from here, you're down to 69 inches, which is x bar minus 2 s's. That means all the data that you guys guessed, all of your weight guesses are within the 2 standard deviations. Nobody guessed too low, nobody guessed too high. Please, Lauren.
So the 1 inch, I'm a little bit confused.
The 1 inch?
Yeah, so but we multiply by 2.
Hang on, come back to that. First of all, what is the 1 inch? And tell me what that is again, for those of you that missed this question on the exam.
The average weight from the average.
Give me a little bit more than that. Just a smidge more. The average what?
One data point.
The average, give me one more D word. The average distance
Away from the
of
average.
data points away from the average. That's what the 1 stands for.
Okay.
So once you know that data points are bell-shaped, then you get percentages. So not only can you say it's the average distance away, you can say at least, or I should say at least, around 2/3 of the data are within 1 inch of the average. Around 95% of them are within 2 inches of the average.
So from the 2/3, it would be between 70 and 72.
70 and 72, that's about
And
2/3.
2 standards it would include follow-up.
Yes.
We're supposed to do 2 standards.
That's industry standard for statistics.
Okay.
Industry standard is if you got bell-shaped data, 2 standard deviations, that's your fence, that's your range that Serenity was talking about earlier. It slaps up the fence at 2 standard deviations and says anything outside of this is unusual. In other words, you guys didn't have any unusual data values based on what you said. 69 was not too small, and 73 was not too big. They were the biggest and the smallest, but they weren't too big or too small by this method. I'm not saying this is the be-all and end-all. I'm saying if you use this, which most statistical research journals will do, it's all within a normal range, a typical range. No outliers, no Jareds, no 51-year-old grandmothers of 3. There you go. You're all within your fences. Make sense so far? Ask me questions on this. I want to take about 5 minutes over, but I want to make sure we wrap this up before I want to collect some more data too. But I think I can force a non-bell curve on you guys. I think. Richie.
If we had somebody had guessed 68 though, they would have been.
Now, good question. And I want to come back to what Serenity said earlier. If somebody had guessed 68, if we just drop that onto this graph, that would be an outlier. But you'd also have to do what here? That would change your average and your standard deviation a smidge. It would lower the average a teeny bit, and it would raise the standard deviation a teeny bit. I'm not sure if it would raise it enough to be a meaningful difference, but you can't just slap it on, you have to recalculate too. Is that fair?
Yeah.
Yes. Now, if somebody had guessed 60 or 63 or something like that, I think we could arguably guess that would be. And this goes back to somebody in the last class said, just look at it. It's fantastic. You guys looked at that immediately and said there are no outliers, and you were all correct because it looked correct. There were no gaps, no weird jumps and things like that. It was fantastic, absolutely fantastic. The problem is that if you have to quantify the unusualness, you need to have an analytic, a metric to put it against. There's one of them. There's one more. Let's talk about after the break. Yes, you guys got that glazed look. Yeah. Take a walk, get some air, get some water.
Your shoulders.
Okay, Carol.
Yeah.
It's like it's